Hey everybody, this is Mark Durrenberger. I am president and founder of New England Clean Energy, and I have this little presentation I like to call the magic of heat pumps. I've presented this set of slides to the Home Builders and Remodelers Associations both in central and eastern Massachusetts, and it was part of some larger training I did, but I thought I'd extract this to help everybody understand how heat pumps work. So let's get started. Step number one, I got to give you a key concept. It's called energy units, and that is how do we talk about energy or the amount of energy that we're using on a project. So the key term that most people have probably heard is something called a BTU, or British Thermal Unit. If you ever wonder, British Thermal Unit is the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. Aren't you glad I told you that? Anyways, another unit that gets used a lot for describing energy is kilowatt hours. You see that on your electric bills. That's the common energy unit from National Grid, Eversource, or whoever provides your electricity. Joules is another energy unit. You don't see it too much, but in the world of physics, they use those a lot. And even in medical applications, they use a joule. For example, I learned from one of my customers that a pacemaker jolt is rated in joules. Again, another useless piece of information for most of us. The nice thing about energy units is they're easy to convert from one to the other. Just go to the internet and say, hey, how many BTUs in a kilowatt hour? And you'll get an answer right away, 3,412 as it turns out. Okay, so now let's talk about something else that's really important called efficiency. Efficiency, and I'm going to limit it to the context of heating and cooling. It's a measure of how well a heating system uses its energy that you feed it. In other words, if you put in 100 units of natural gas energy, how much useful heat will you get out of that 100 units of natural gas? It's only applied to fossil fuel heating systems because you're converting from a stored form, the fossil fuel, to heat. The equation, really simple, efficiency is useful energy output divided by energy input. And an important thing to note is that efficiency can never be greater than 1.0. See the footnote on the second law of thermodynamics. And if you're having trouble sleeping, go to the Wikipedia and look up the second law of thermodynamics. Okay, now, what is a heat pump? Fundamentally, what a heat pump does is it moves energy. It does not convert like a traditional furnace. They're quite common. You have them already. Refrigerators, freezers, air conditioners are heat pumps. And of course now, home heating and cooling systems are heat pumps. They've been around for a while, even for home heating and cooling, but they've become very popular, particularly because they've gotten so much better. So, what are the configurations for heat pumps? The two different common configurations are ground source heat pumps, also known as GSHP or geothermal systems. What they do is they move energy to and from the earth. The nice thing about the Earth is it's a nearly constant temperature year-round. So if you go down deep enough, the Earth is pretty much around 50 degrees all the time. What that means from a heat pump standpoint is that their performance is pretty consistent year-round. However, geothermal systems are pretty expensive to install because either you have to drill in wells to get down into the ground, or you have to bury many feet of horizontal piping. And you need space as well for that sort of stuff. Air source heat pumps, on the other hand, or ASHP or mini splits or split systems, move energy to and from the air. However, air temperature varies constantly, particularly between winter and summer, and that affects the performance of the heat pump. The good news is they're far less expensive to install, and it's gotten to the point now where their performances are acceptable and quite competitive with most fossil fuel heating systems. The key concept with a heat pump is how you measure its performance or heat pump performance. We do not use the term efficiency because it doesn't apply because we're not converting a fuel. Instead, we use something called the coefficient of performance, or COP for short. And the equation for COP is useful energy moved divided by energy input. And because heat pumps move existing heat energy, the COP can be greater than 1, unlike efficiency. So, you get a heat pump and someone says, oh, it's got a heating COP of 3.0. What does that mean? Well, what that means is you input 1 unit of energy, let's say 1 kilowatt hour, and that heat pump will move 3 units of energy, or 3 kilowatt hours. If you wanted to convert that to BTUs, that's just over 10,000 BTUs. But manufacturers don't usually tell us the COP, but they are required to publish something called the Seasonal Energy Efficiency Ratio. The acronym is SEER2, because there used to be another version called SEER. Then I use that one for cooling. And then there's Heating Seasonal Performance Factor, or HSPF2, for heating. And to convert either of those numbers to a coefficient of performance, you just multiply them by 0.293. So if you've got a heat pump with an HSPF2 of 10, the coefficient of performance is 10 times 0.293, or 2.93. And if the SEER2 is 16, the coefficient of performance is 16 times 0.293, or 4.688. And since HSPF and SEER are seasonal average values, they represent the seasonal average coefficient of performance as well. So when you're doing your heating and they give you an HSPF of 2.93 or 10, and you multiply by 0.293 to get 2.93, you basically say over the heating season, the coefficient of performance for that heat pump is 2.93. But you also have to be careful that you're using HSPF2 and SEER2, and you have to use the numbers that represent your climate zone. Here in Massachusetts, we are climate zone 5, and that dictates a certain ambient temperatures in the winter. Climate zone 4 is somewhere around Virginia, and heat pump performance is different in climate zone 4 versus climate zone 5. Now, how do these things work? So here's an example of a heat pump in heating mode. What you see in the middle of the chart is a 1 kilowatt hour of electricity, and that's driving a compressor. That's an electronic device, and running through the system is a gas. Normally at room temperature it's a gas, and room pressure. But when you compress that gas, you're basically forcing a whole bunch of these gas molecules to become really close to each other, and normally they have a lot of energy, and that's what keeps them flying apart as a gas. And by compressing it, you're squeezing all those molecules of that gas into less space. And in order for the gas to do that, it has to give off energy. So by compressing that gas, you're dumping energy. And if you do that in a heat pump system, you're effectively compressing it on the inside of the house. It's dumping the heat as you compress it. Basically, you're converting that gas down to a liquid. Then you pump that liquid outside and you let it expand. In order for that gas to expand, it has to draw energy from the atmosphere. And the example I use here just shows a heat pump with a 1 kilowatt hour of electricity going in, and you're moving 3 kilowatt hours of thermal energy. So that would mean a heat pump with a COP of 3. Okay, now what happens in cooling mode? Guess what? You're just reversing the process. And heat pumps have these reversing valves, and they switch things around. So now what you're doing is you're dumping that kilowatt hour of electricity, but now you're compressing the gas outside the house. So it's dumping heat, and then you pump a liquid into the house and you let it evaporate back into a gas. And when it evaporates, it has to draw energy in order to evaporate. And then you draw that energy into the liquid, which then goes back to being a gas, and it goes outside and you compress it again. Anybody that's put their hand on a compressor tank, an air compressor tank, you know compression makes that tank warm, and it's the same exact physics. If we look at a real life example, I pulled up a standard cold climate LG 36,000 BTU heat pump. My sons had this installed at their place across the street from where I live a couple of years ago. And I found the specs for that heat pump. It has an HSPF2 rating of 9, or put another way, its coefficient of performance for heating is 2.65 in climate zone 5, which is where we live. And its cooling coefficient of performance is based on the SEER2 of 22, or 6.44. And the nice thing about SEER values is they are not climate zone dependent. But 6 kilowatt hours of energy out for 1 kilowatt of energy, and that's an amazing amount of energy moved for the amount of energy you put in. By the way, they talk about heat pumps. A lot of times a sales guy will come in and say, oh, you need a 3-ton unit. And you're scratching your head. What does weight have to do with heating and cooling? Well, it's an old cooling metric, probably invented by a guy named Carrier. You've heard of him, right? Carrier air conditioning. Anyways, a ton of heating, particularly cooling, is the metric that was introduced based on how much cooling you got out of a ton of ice, or 2,000 pounds of ice. Yes, another one of those useless sort of data points for the back of your brain to impress people at parties. Okay, now remember I said that heat pumps performance varies with temperature? Well, here is that same heat pump's performance curve in heating. And if you look at around 20 degrees Fahrenheit, the coefficient of performance is slightly above 3. If you went down to about 0 degrees Fahrenheit, the coefficient of performance is around, oh, it looks like about 2.9. But if you went up to about 40 degrees Fahrenheit, you'll see the coefficient of performance is somewhere about above 4.5. So yes, as it gets colder, the performance of the heat pump drops. And as it gets warmer, the performance of the heat pump gets better. Okay. On the cooling side, I get asked often, why are heat pumps better than regular old window air conditioners? Well, there's a couple of reasons. First off, they have a DC motor, which means they have an inverter that converts AC to DC. And DC motors can be controlled very precisely, both the speed and on and off. You can start and stop it quite quickly, and it can bring it up to speed and go slower speeds, higher speeds, whatever. So when the cooling demand is really high, they run at a high speed, and when the cooling demand is low, they run at a low speed, and that results in a huge savings in electricity. Another factor is that the condenser and the evaporator are separated. That means you don't have heat from the condenser poisoning, if you will, the evaporator. So the two components don't share energy because they got one component's outside, the other component's inside. Commonly, we want to compare heat pumps with fossil fuel. So I did this quick math. This is based on conditions as of February 2026 in my service territory where I have National Grid for electricity. My electricity is about 35 cents a kilowatt hour. Let's assume that the heat pump I'm putting in has a heating coefficient of performance of 3. Oil at the time is $3.75 a gallon. Yeah, I know if you buy it in the fall or if you buy it other times of the year, the price will go down. But buying it this time of year, it's expensive. Oil heating, usually the best you're going to see with an oil furnace is about 85% efficient. Part of what destroys the efficiency on oil furnaces is that the heat transfer components get coated with soot from when they burn the oil. And of course, the other 15%, where does that go? It goes up the chimney, carrying away carbon monoxide, carbon dioxide, and all those other nasty things, and a little bit of heat gets wasted. Natural gas, it's about $2.03 per 100,000 BTUs. That would be from National Grid or from Eversource or whoever provides your gas. And gas furnaces tend to perform a bit better than oil furnaces because you don't have that soot problem. So here's the math. I'm going to buy 100,000 BTUs worth of heat in natural gas. I'm probably going to pay about $2.26. So even though it's $2.03 per 100,000 BTUs from the utility, I'm throwing 10% of that out the chimney or the stack or the vent. And so that brings the net cost up to about $2.26. So yeah, it's the cheapest one. A heat pump, that same 100,000 BTUs with a COP of 3.0 on my heat pump is going to cost about $3.07. And then an oil with an 85% oil boiler, and you're paying $3.75 a gallon. It's about $4.41. So that ranks number 3. So I'm not going to deny it. Natural gas is cheaper when it's cold. The downside to natural gas, pricing is volatile, and of course it produces CO2, which doesn't help the environment. Then if you look at the heat pump curve that I showed on a previous slide, it turns out that when the ambient temperature outside goes over 38 degrees Fahrenheit, the heat pump actually costs less than natural gas. And as I said, heat pumps are great in the shoulder months, spring and fall months when you're heating and it's relatively warm outside. So you will see some systems out there that have hybrid, where they switch between natural gas and electricity and do their heating based on whichever one's cheaper. Those are kind of expensive systems, but they are out there. The trade-offs, of course, you get great cooling from heat pumps. So your cooling costs go down, maybe your heating costs go up when it's really cold, but in general you're gonna be ahead, and you're not putting any more carbon dioxide into the atmosphere from your own heating plants. So in summary, in cooling, there's no better solution than a heat pump. That's why they've been in refrigerators and freezers forever, right? For heating, on the coldest days, natural gas is the least expensive, but the shoulder months, spring and fall, where electricity is inexpensive, the heat pumps usually win. For example, I used to live in Hudson Light and Power. The electricity there was about 13 cents a kilowatt hour, and I did the math, and it would have been cheaper to heat my house with heat pumps than to heat it with the natural gas that was there. However, we knew that we were moving, so it didn't make sense to convert the house over. Though the new owners, they might take a harder look at this and say, hey, yeah, it makes sense for us to convert. That's up to them. Usually heat pumps beat oil. It depends on when you buy the oil and what you're paying per gallon. And they almost always beat propane, even in the colder weather. And the good news is the heat pumps continue to get better. So that's all I have to say. Thanks for watching. If you're considering adding a heat pump, give us a call. We have several folks who can answer your questions. And like our 20 years of solar installations, we do great work and we stand behind it. Thanks very much.